My name is Jaydev Desai. It's my pleasure to introduce our seminar speaker today, Professor Tim Kowalewski from University of Minnesota, where he is currently an assistant professor. And he graduated from Blake Hannaford's lab at University of Washington, for those of you who might know Blake Hannaford. And he's currently, one of the things that he is actually very well known for is the whole notion of evaluating how good a clinician is when they're doing a procedure. And so skill evaluation is one of his forte, and we're going to hear a lot about it today. He also commercialized his PhD work for quantitative skill evaluation, and this is basically the CSATs that you probably might have heard of. Today we're going to hear from him about computational surgery, so helping surgeons avoid mistakes with better robots. So thank you, Tim, again, for coming over.
Wonderful. Thank you so much, Jaydev, for the invitation. It's been wonderful to actually see your campus and see the amazing projects you guys are working on here, and meet fellow roboticists today and clinicians yesterday. So before I begin, I just want to say two things. I have a little disclosure. One is you'll see some information from CSAS Incorporated. We created a company in this area, so there's a financial conflict of interest there. And the other thing is you might see, so this is a talk about surgical robotics, so you'll see some footage of surgery. And whenever you see that little element show up, I learned my lesson to always do this. Whenever you see this little symbol, that means the next slide is going to have some footage of surgery. And so about maybe less than 10% of the population, they get queasy when they see footage of basically blood and guts. And if that's you, if you see that sign, just look down, check your email, do something else. I learned my lesson because once I gave a talk to a math department and they all got really queasy, and not good news. All right, so let's dive in. Let's start with a little bit of history about surgery. So I really think the field of surgery began as a scientific discipline with John Hunter, who for the first time started using the scientific method in surgery. And that's really where it took off. This is back in the day when, for you to be a surgeon, the idea is you were a maverick. You actually created, part of your surgical training was how to create all of your own tools. You'd make all of your own prototypes. And everything you'd put into a patient was stuff that you made yourself. The application of the scientific method gave a rise of proliferation of progress in surgery, with a rise of anesthesia finally. Some people really think surgery really only started once anesthesia was getting used. It was only in the 1850s that Semmelweis did his work scientifically proving that surgeons should wash their hands to avoid spreading infection. And he was actually met with a lot of ridicule at the time. People thought it was a useless idea, but scientific evidence won out. This is before germ theory, and things really picked up. And then ultimately, the way surgery was trained is still the way we do it today. You have, you go to medical school, you get a medical degree, an MD, and then if you want to be a surgeon, you go into residency for maybe 4 or 5 more years, maybe 10 if you're doing neurosurgery, and it looks kind of like this. You have an attending surgeon looking over you, you're doing a task maybe for the first time, and he lets you do it, or she lets you do it until you make a mistake. And the idea is you see one being done, you do one until you make mistakes, and then you start teaching them. And that's called the Hallstadian model. It hasn't really, it's remained largely unchanged until the last decade or so, because the field of surgery has been changing. This historical perspective where you had open surgery, where the surgeon was directly interfacing with a patient, right? In open surgery, the connection is one-to-one. You see in the left half picture. In the 1980s, surgeons started working with engineers to create new tools. You can see these long, slender tools here called laparoscopic tools. The surgeon got further removed from the patient, but this was a major benefit to patients. Instead of going, having an open procedure for, let's say, a removal of an appendix, you had to stay in the hospital for a few days afterwards. Laparoscopically, you can go home within an hour because it's so minimally invasive. And then fast forward to today, where the Da Vinci surgical robot, you can see the geometric, almost exponential rate of adoption of this technology, where the surgeon is actually completely removed from the patient. They could actually be transcontinentally removed across an ocean and doing these procedures. It's been done before. This sort of geometric rise was actually due to urology. So today, we haven't actually seen this penetration of robotics in cardiovascular or cerebrovascular. Much larger markets, much bigger opportunities. But notice what's going on. Not only have you now removed the surgeon even further from the patient, there's no force feedback. They might be in different rooms. Something else has also crept in. That traditional interface has been replaced by a digital interface. So everything going from the master console is fiber optic digital signals, about 128 dimensions of data running in real time. And so sometimes you don't even need a patient. So increasingly what's happening is surgeons are training in virtual reality or in simulators. So you make your mistakes there instead of on humans and get your skills quantified before you actually go on a human being. You see here some work on a virtual trainer. Or this is just grabbing real surgical tools, doing a mock dry lab task, and measuring your skill. So in the words of Rick Satava, it's no longer blood and guts, it's bits and bytes. It's a classic quote from Rick Satava, one of the sort of godfathers of modern surgical robotics. And that's really the field of computational surgery, which is really exciting because for the first time, the field of surgery is now rigorously quantitative, or it can be. And we can use methods from machine learning, from systems engineering, system science, to grapple with problems in healthcare. Long-standing problems with healthcare. So it's an exciting field because it's potentially going to do some great things in the field of surgery. So let's look at some problems facing healthcare. Like what kind of stuff could we potentially help with? So at the turn of the millennium, this publication came out, landmark publication from the Institute of Medicine, where the field of medicine, of healthcare as a whole, took a really cold, hard look at itself using numbers and not opinions. What they found was that the rate of iatrogenesis, that is human error, preventable human error, was rampant, and those medical errors led to approximately 100,000 deaths a year, preventable medical errors, and about $30 billion of annual costs. About a third of that was surgery, even though surgery is nowhere near a third of healthcare, but they're responsible for a significant portion of those errors. Consider that the average American has 7 surgeries in their lifetime. This is a risk that we're all kind of exposed to. Consider also that, well, I'll back up in a second. When this came out, this was somewhat earth-shattering because nobody really expected these numbers were so high. So there are major policy shifts in healthcare. Things like the wait list, the checklist manifesto came out, where surgeons learned from pilots that one of the best things that pilots have done to avoid trouble in landing and takeoff is they'll just go through checklists. And they started incorporating that. But despite all these massive shifts and policy changes, these error rates kept creeping up. There kept being publications that would come out that actually show the numbers keep increasing, and people would discredit those publications because they weren't published in very reputable sources until last summer, the British Medical Journal, a very reputable source, dropped this bombshell. That in fact medical errors were so grossly underreported that they're actually, when computed correctly, they account for roughly the 3rd leading cause of death in the United States. Which is phenomenal, which means that medical errors are rampant. We're talking about, a surgeon taking out the wrong kidney, a nurse giving the wrong dose of IV, the pharmacist prescribing the incorrect medication or passing out the incorrect medication. So this is a pretty serious problem. And healthcare has been trying to grapple with this problem for millennia, the fact that human error is rampant, and surgery especially is very difficult, let alone medicine. So let's dive in. Caution, there's going to be some footage. In 2013, Birkmeyer and his colleagues, writing in the New England Journal of Medicine, hypothesized that if you measure the technical skills of a surgeon, it would correlate directly to patient outcomes. Shown here is footage from 2 of the surgeons in his 20 bariatric surgery study. These are practicing surgeons. This is their full-time job, their bread and butter procedure. And he asked that they voluntarily take one video of their surgery and submit it to their peers for anonymized assessment of their technical skills. So you can decide here who you'd prefer to do your surgery. This is a top and bottom quartile performer. What they found was that as the technical skill rating increased along this axis, the risk-adjusted complication rate decreased. So much so that if you were in the bottom quartile of performers, you had a 5-fold increase in death, a 3-fold increase in blood loss, and a 3-fold increase in hospital stay. Nobody anticipated that technical skills would matter that much. And again, this is for practicing surgeons. This is not trainees. This is not residents. And again, that was from one video. It could project the outcomes, surgical outcomes, of that surgeon's entire year of practice, which was pretty interesting. So how hard can this problem be, measuring technical skill? I want to show you 2 surgeons. These are actually residents, but they are doing surgery. And I want to ask you as quickly as you can to tell me who you would prefer to do your surgery. Anybody want the person on the right? So notice you didn't have to wait the 10 minutes it takes this person to actually finish this task to tell. Within seconds, you can tell. You don't need a medical degree to tell that one of these individuals looks more skilled than the other. Interesting. Well, can we quantify that? Can we do something a little bit more rigorous and scientific instead of just that gut feeling? So the videos that you just saw, we were actually capturing the tool motion for the surgical tools. This is what they look at, like plotted out in time. You can see a lot more sort of entropy and chaos in one versus the other. But this is still pretty qualitative. This is still not an actual number. And you can look at things like the force profile of grasping. So on the top here, you have the left and right hand grasping of somebody we called an expert. We'll get to that. And it's not that the expert has less force or more force than the novice. It seems that they have a lot more consistent force behavior, and the novice just has a lot of variability. So anyway, these are sort of nice observations, but they tend not to scale very well to, let's say, looking at 100 surgeons, maybe comparing two very extreme cases. We need something a little bit more rigorous. And so for this, we collected some massive databases. They're called Blues and Red Dragon Edge. I won't get into those details, but we have over 50 hours of these procedures recorded where we have tool motion and video. And the idea is, can we quantitatively measure the skill and do so better than a stopwatch? So it turns out that measuring how long it takes somebody to do a task, that's very hard to compete with. A good surgeon can do stuff more quickly, period. And if our skill metric, our machine learning amazing skill metric, gives you nothing better than the correlation to a stopwatch, it's useless. You can get a stopwatch for $10 and you're done. And so what we try to do is have a quantitative measure of skill that's better than a stopwatch. So in 10 seconds, can you tell me how good skill is? Just like you guys could. And that's been kind of underexplored. And so a little bit of footage coming up. So what you see here is our early work, a machine learning, this is just a hidden Markov model being trained in real time on the live surgery that you see running here. Evaluating in real time, pre-trained on the surgery that you see here. And this allowed us to actually quantify the skill of a surgeon. I won't get too detailed into the method. It's just pretty much boilerplate hidden Markov models. And I applied this in my PhD work, and I was actually disappointed because it didn't work very well. Like, yes, you could disambiguate surgeons, but when you take the first 10 or 20 or 30 seconds, it didn't actually work. And I got really confused. I was like, well, why would that be? So I started questioning the assumptions that the surgeons gave us. They told us who the experts were. They said, hey, these guys are the best in our department. This guy's the maverick. Use him. And I trusted them. I said, OK, I'll use this as my ground truth labeling. And I started to get really suspicious of that. So what I did is I took 56 of the videos. I took what they use as their gold standard. So this is an example of a tool called OSATs. It's Objective Structured Assessment of Technical Skills. It's just a set of Likert scale domains. So on a scale of 1 to 5, how well do you use both hands? On a scale of 1 to 5, what's your tool motion efficiency? How confident are you? That kind of stuff. And this has been validated in the surgical literature. This is a tool that actually faculty surgeons will use to evaluate their residents before they're accredited. Anyway, I sat down my surgeons, my collaborating surgeons, and I put in front of them 56 videos, and I asked them to evaluate these surgeons as if they're evaluating their own students, be as objective as possible. What I didn't tell them is that the 56 videos they were looking at were videos of all the people they told me were the top experts. And they proceeded to disqualify over half as non-competent surgeons, which was interesting. At first, I was kind of shocked. I didn't really know what to do with that. Here we define competence, so you had to have both a score above 3, so the average score for motion quality, and above 3 for bimanuality, and there were very few that actually ended up in both. So we were suspicious of those results, but when we finally used a true sort of ground truth that wasn't noisy, then the skill evaluation really worked. So the machine learning problem is very ill-posed. If you have two sets of data that are very noisy, so let's say you have labeled data, and you sort of cross-contaminate a bunch of those labels, any machine learning algorithm is not going to work very well. So when we got a better ground truth, it worked, and we could actually identify a skill within, I think it took 40 seconds to disambiguate novice from expert behavior for a task. And then the cool thing was, at least for these 3 training tasks, and these 3 tasks, by the way, are correlated with surgical outcomes, surgical performance. And the cool thing is, it's a hidden Markov model, so we can crunch this in real time. So for every frame, every 10 milliseconds or so, every 5 milliseconds, you can ask, are you doing good surgery or poor surgery? How well do you fit the model? So what you're seeing here is a probability that you're acting like an expert versus the probability that you're acting like a novice on that expert video that you saw. And what happens is sometimes you're looking like an expert, sometimes the model doesn't know, sometimes it's confident that both of them are doing the same thing, so you can't really use that information, and then sometimes it inverts. Sometimes a person starts acting like a novice. And this is the other problem with the ground truth data, is that for an hour of surgery from an expert, for about 10 seconds, he'll slip up and do something not very good. That's going to pollute your ground truth labels. And a novice, like for 3 seconds, they can get lucky and just look awesome for those 3 seconds. And that, again, pollutes the data. So we had this problem, we ended up coming up with this thing called the minimally acceptable classification criterion. So one is you have to provide something over task time. It's got to be better over task time. Well, great, we can get real-time metrics. This I won't get into. We published recently that it takes about 10 to 15 seconds of data from the beginning, and machine learning will give you everything you need in the 10 to 15 seconds. It's not going to give you much more improvement to crunch on the entire task. And then here was the harder one. We said that machine learning will fail unless you meet this criterion. If I show you guys an obvious novice, somebody that should not be touching a patient, versus an obvious expert, you will unanimously agree that these are extremes of the category, right? And so our minimally acceptable criterion was that a machine learning algorithm has to be able to give you that 100% accuracy in that no-brainer case. And what we found is that every single machine learning algorithm technique that we've employed or our colleagues, competitors in the field have employed has failed to meet that, which is interesting. Maybe it's because there isn't enough information in the tool motion, maybe because we don't have enough machine learning background, but it seems like if we can't even disambiguate this basic case, there's no point in going further. Also consider that there's 51 million surgeries done in the United States every year by about 100,000 surgeons. And the majority of those are not robotic. We don't have data for. But those big errors are happening with these big numbers. How do we actually get a method that can scale and be correct to those big numbers? So can we actually scale this? Can we do objective assessment and scale it accurately? And this is where we propose this somewhat controversial hypothesis that you guys seem to tell me very well within 10 seconds who was a better surgeon. And so we had this idea, well, can we just crowdsource this to non-experts, aggregate their ratings, and will they be equivalent to ratings by top experts? So crowdsourcing has been around for a long time. It was founded by Lord Francis Galton, the sort of grandfather of modern statistics, in a 1907 Nature paper. It's an interesting story. This is his story of the ox, where he was. It's kind of a controversial story. He was actually a eugenicist. He was trying to prove that there's a better class of human beings than another, and he wanted to scientifically prove that you shouldn't let the average person, for example, vote because they're uneducated and incapable. And so he found a little carnival where the game was somebody would bring out a huge ox, and if you could guess the rendered weight of the ox, how much it weighs after all the good stuff is butchered, how much does that weigh, to within a pound, you get it. And people were lining up by the hundreds. And he's like, aha, I've got my experiment. So he got somebody to tabulate all the guesses. He went home, analyzed it. Nobody was even close. So he was going to say, OK, finally, I can sort of quantify how wrong people can be. But when he computed the median, it was within a pound of the exact rendered weight of the ox. And that's, by the way, the founding of the central limit theorem, where if you sample from a distribution of any size, it doesn't have to be normal, and you keep averaging, or you keep aggregating, or taking the median, that distribution is normal. And all you need is enough data, n equals 30 or more, and you'll converge to the true mean. And this has been around again for a while. It's kind of like a fad. It comes and goes every 10, 20 years. Recently sort of reviewed by Surowiecki in this book. One of my favorite cases is where the folded group in Stanford has shown that you can get crowds of non-experts to outperform groups of top PhDs on a complex protein folding problem that the crowd doesn't even understand. But on average, they could actually outperform them. So who are these crowd workers? Over 6 million are ready to work at any time through platforms like Amazon Mechanical Turk and others. More than half are female, more than half are educated with an advanced degree. And that means that they are sufficiently diverse large to meet the criteria for Francis Galton's crowdsourcing. As long as your variables are independent and aggregated, you're going to be good. So here's how we tested the hypothesis. We gave a bunch of crowd workers this 1-minute video. This is a video of a robotic training task, and gave them the same exact survey instrument that faculty experts use, and asked them to objectively quantify the skill on exposed here. Had no idea what we were doing. We gave them $1 to look at this task, which turned out to be way too much for these people. It turns out there's a lot of people with a massive amount of free time on their hands that want nothing more than to do tasks for you for 10 cents on Amazon Mechanical Turk, which is great. And I kid you not, the more you give them, the more they tell their friends, and there seems to be no bottom to this. So then we tested the hypothesis. We got the scores from the Turkers, and we got the scores from 10 faculty experts. And let me draw your attention to this. The means of the two were statistically identical, pretty much, just like the Francis Galton study, which to us was really surprising. We had question mark, exclamation point. We didn't really trust us at first. What was even more interesting is that it took less than 24 hours to get the 400 ratings from the Turkers. Again, they've got nothing better to do, and they're around for 24/7. Whereas it took almost 24 days, almost a month, to beg and prod and plead 10 surgeons just to watch a 1-minute video and give us the rating, even though they're involved in the study. But this sort of underscores the problem. Faculty surgeons, they don't have the time. They do not have the time to sit there and give their trainees all the attention or evaluation that they need. All right, so we published that. I remember presenting it at clinical conferences, and it would just immediately polarize a room. Nobody would be like, oh, okay, that's interesting. You were either, that is amazing, we need this yesterday, or the other half would be like, you're insane. Nobody's going to evaluate my skills with a group of Homer Simpsons off the street, right? But the central limit theorem says that statistically this is going to work. You're going to converge to the true mean. Then the feedback we got is yeah, but look, this is a simulation task. This is not surgery. What about when you go to live animate surgery? Surgery is so much more complex. Everybody gets what's supposed to happen here. So here comes some more live surgery. The first study where we actually tested on animal cases, we had 12 porcine bladder closures. So these are pigs being used to train surgeons to use a Da Vinci robot across a variety of skill level. You can see the ratings from the surgeons, the faculty, aggregated on this axis. So for each dot, you have about 5 to 12 surgeons that we're averaging their scores for, and the crowds, about 30 to 50. And we got a Cronbach's alpha of 0.92. Cronbach's alpha is a measure of concordance, kind of like correlation. But numbers of 0.9 or above are considered good enough for high-stakes assessment. So we were really, really surprised by this. When we actually went to live surgery, we got better numbers than when we were doing simulated tasks. And again, the concordance was strong enough to actually merit some really thorough study. And people sort of caught wind of this. We ended up getting lots of phone calls from all sorts of people, like the American Urological Association. They had this massive study where they're trying to validate a new curriculum to credential their surgeons. And they ended up with 454 videos to evaluate. And there was, in the words of Elspeth McDougall, the director of education at Urology, never in my lifetime will I get my surgeons, the people that she's the boss of, to evaluate that many videos. So they turned to us, and I'll just kind of skip through this. We got really good agreement with their experts, and long story short, they ended up using the crowd scores to validate their entire curriculum for the entire American Urological Association. And they were able to, so in about 9 days, we actually evaluated all those videos, over 16,000 ratings in 9 days, which is, now we can actually scale up to those numbers, 100,000 surgeons a year. We've published this in repeated locations. There was a recent sort of summary of some results from JAMA Surgery. But other people have now really picked this up. There's now actually a review paper written by a clinical group about all the people using crowdsourcing in healthcare, started from this stuff. Then the first real study we did on live human cases was with this group, the Michigan, it's called the MUSIC group. You can see what it stands for up there. It's actually really remarkable consortium. Over 90% of all of the urologists, urology surgeons in the state of Michigan, voluntarily, nobody's forcing them to do this, voluntarily pool their outcomes resources. So they'll pool things like, how they're doing just for the sake of self-improvement, which is really remarkable. So we partnered with this group. They're running a study to try to replicate Birkmeyer's work, to try to replicate the Birkmeyer hypothesis. And the hypothesis was that our crowds would be concordant with their experts. So 12 videos were assessed. And what we found was, as they ranked the scores from the expert reviewers in the middle column, and the scores with the reviews from the crowds in the far right column, they agreed on the bottom 5 performers, which was interesting. Now remember, these are live cases on humans with outcomes, and we are showing agreement between crowds that did this very quickly and expert surgeons, which was remarkable. Now, it actually worked a lot better than we anticipated, but you could also see there's some disagreement in here. So for example, they don't agree on the top performers. And people will say, well, yeah, but the top performers don't matter. What we're worried about are the people in the bottom quartile. Those are the people we need to help with more training. But we started getting suspicious because statistically, the statistics is in favor of the crowds. That's where you have the high power, the high numbers. So we started getting suspicious about these expert scores. Like maybe the gold standard in surgery is actually not the ground truth. Maybe the gold standard that they think is the best thing for skill is not accurate. So remember, we're using a survey tool for all this stuff. And so the clinicians are using the same web survey tool. Every mouse click, we're recording. So we got suspicious. And for an average video of 13 minutes in length, we looked at how long it takes the faculty to review it versus how long it takes the crowd workers to review it. And we caught them in the act. The faculty weren't even watching the whole video. They were barely watching a half. Whereas the mechanical Turkers, again, they're spending more than 13 minutes watching this video, getting really excited about putting in comments and that kind of stuff. So clearly, this is not the gold standard. What if they missed something in the middle of that video? And for all we know, maybe the faculty, maybe they only need 10 seconds to tell you exactly the skill. So this doesn't say that they're making a mistake here. So if we're trying to compare gold standard to ground truth, we really need some sort of arbitrator. And what is that? We have crowds versus experts, who's correct? And that's where we bring in patient outcomes. Patient outcomes are the trump card. Like, does this actually benefit patients? Can you predict improvements in outcomes for patients? And that's a much harder problem. But we've been working with a number of hospital networks, and we've been collecting this data in long term. And we've been able to show, again, this is with CSAT, so disclosure there, Incorporated, the company. We've been able to show that the CSAT scores correlate directly to patient outcomes. So if we have crowd workers looking at your video, we can correlate to hospital readmission rates, excess blood loss and length of stay, and significant complications. What was even more surprising, so it seems like the crowds agree with the outcomes, and the faculty agree with the outcomes as well. Though in this study, in certain cases, the crowds actually had better predictive power of the outcomes than the experts, which is interesting, which was a surprising result to us. And I'll just wrap it up here. This thing has spread like wildfire. There are now entire hospital networks that are actually using this. I'll just highlight 2 of them here. One is Adventist Health. That's the 6th largest hospital network in the United States. Within 2 years, every surgeon will be evaluated by this. And by the way, it's not the surgeons evaluating this, it's the risk assessment department. Every hospital, every major network has a risk assessment department. They have budget and a mandate to minimize risk, to improve outcomes. And they don't have tools to do it. So they got a hold of this, and they're going to implement this over their entire network. And within the 3rd year, they will make credentialing decisions. They will grant or revoke operating privileges based on these scores. I'll also mention briefly that we've been able to show that this works in not just high-profile research institutions or expensive hospitals. My colleague Lee White, who's now at Stanford, actually did this on a fellowship in Ethiopia. So he went out to a local clinic, got a local smartphone that he got off the street, took a bunch of videos, and he showed that there, for their medical school on suturing, he can get the same level of accuracy as Stanford Medical School for skill evaluation. So I'll just end the skill eval part with this. The problem of quantifying surgical skill in surgery is not closed. It's not done. I think we've just started. And for machine learning, it's been data starved for this entire time. We can't actually solve the problems with machine learning until we get really clean data. But I think now we're finally getting to the point where we have massive databases. They're very well labeled. They correlate to outcomes. and now we have a well-formed problem for machine learning. So we're putting together this DAX alliance. If you're interested at all, we're going to actually put these on public forums. So machine learning experts, you just get the data, you get the labels, and see how well you can make your algorithm perform. And we'll have like an annual contest where we'll give out $10,000 or something in a prize. So if you're interested, please email me. We'll put you on the list of people when we actually publicize it. All right, that's the first half of the talk. First part of the talk, the major part. The other part is this. Well, look, even if we make every single surgeon an absolute expert and a master, they'll still make mistakes. Humans make mistakes. Can we ever get that risk all the way down to zero? Because human error is guaranteed. We're just human. And so that's where this idea sort of comes in. So we've seen how the surgeon-patient interface is getting replaced by a digital interface, and the rise of co-robots. So if you've got a surgical robot, you're at once a co-participant, a co-worker with a surgeon, but you can start acting as a co-defender to the patient. What if a robot could actually detect an imminent error about to happen, and not just alert the surgeon, because they could ignore that, but actually prevent it from happening in the first place, or by design make it impossible for an error to happen. So this is kind of our goal, is an error-avoiding surgical robot. And the idea is you detect something in real time before it happens, and you automatically prevent it. And we started with a very non-controversial area. So if you go to surgeons and tell them, look, we're going to take control of your motion trajectories, they will have issues with that. That's very controversial. Historically, the surgeon is like a deity in the operating room. They are in command of everything, absolute authority. And challenging that is quite controversial. So we decided to go with a non-controversial problem. It turns out when people use surgical robots, in practice, there's no force feedback, so you crush tissue all the time. Tissue crush injury is far more prevalent with a surgical robot. You have about a 50% increase. Just from using a robot, you'll get your tissue crushed. Nobody's really dying from tissue crush injury. It's just really uncomfortable during recovery, like bowel crush injury. So our hypothesis was that we could, in real time, using the data that the robot already has, no new sensors, using the robot data that's already present, identify what tissue you have, and based on that tissue, throttle the force so that you get the traction that you need, but you don't crush it. And here comes some live footage, careful. And the idea is, you can see the in vivo case here. We've got a surgical robotic grasper, and as it's grasping, during that early part of the grasp, we're just crunching on the data, trying to automatically prevent the crush injury from happening. We've got some models in place. So the field of biomechanics has a bunch of classic work on static models, nonlinear models that look like this. And the problem is, early on in the curve, you can't disambiguate the difference between, let's say, a liver and a spleen. But if you build in a dynamic model, a real-time dynamic model with time derivatives and whatnot, there's a lot of discriminating information that happens much earlier. And think about this. A surgeon's coming in, they're going to grasp. You have maybe 100, 200 milliseconds to identify that tissue before it's too late. So if we're using this, it's not going to work. We need to use some nonlinear dynamics potentially to do it. And then we use this idea. Oh, my computer's freezing up. Restart the program, excuse me. So while that's happening, the notion of shared control. So in shared control, you have a robot that, let's say, is autonomous, and it's kind of like the autonomous driver idea, and a human. Now, right now, the human has absolute control. And the notion of shared control is to, let's open this up. There we go. We're a few in here. All right, sorry about that. Here we go, shared control. Where you have a human driver driving a plant like a robot, which is what we've got now. There we go. Human driving a plant. If alpha, the shared control variable, is 0, the human has absolute 100% control. Standard case in the operating room. If alpha is 1, human gets no control, and a computer or artificial intelligence takes over. And if alpha is any number between 0 and 1, you're smoothly blending. You're averaging or changing in time. And alpha can change very quickly. So we've actually been able to show that this works. You can see here a Da Vinci robot grasper taken right out of the operating room. This was used for some of the in vivo studies. And you can see here, if there's no shared control on, the human will pretty much always grasp too hard. So you could potentially injure tissue that way. But if you turn the shared control on, within about 100 milliseconds, the identification happens. We identify what tissue it is, throttle the force fast enough, and the surgeon doesn't know the difference. We're basically automating this lower level control loop. We're automating low level force control, and they're just grasping tissue, but it's not getting crushed. And by the way, this has been around for a long time, shared control. We didn't invent this, this scheme. And there's a bunch of work in the area, but what we did find is that when we use the scheme right off the shelf, just this alpha scheme, the only requirement is that alpha has to be monotonic with confidence. That's the only real, in between 0 and 1. What we found is that sometimes the system will just go unstable spontaneously, which is not a good thing to be happening in surgery. And what was going on is it's actually really sensitive to alpha dot. If alpha is changing very quickly, your bounds on stability are out. So what we've been able to show is, for example, here is two controllers, two simple, stable LQR controllers. If you blend them in any static way with a constant alpha, it's stable. If alpha changes very, very slowly, it's stable. But if alpha starts changing quickly, you can not only lose performance, you can destabilize the entire system, which seems to me like in the literature, people have just gotten lucky so far with slower experiments. But we ended up stumbling across this because we need alpha to change very quickly. So we have Trevor here is actually working on some theory to use passivity to enable to stabilize this no matter what. All right, but let's move on to a bigger problem. So heart disease is the #1 cause of death in the world, in the US, 1 out of 4 people. That on average is you or the person next to you. The year is 2017, and our best clinical options are still full open heart surgery, coronary bypass, invented in the 1950s, one of the most traumatic procedures, or stenting. So you get a little tube put in to expand the stent. The underlying condition is this: you get you get plaque to slowly build up in your arteries, shown here, that yellow stuff. Starts as early as 10 years of age in American children, depending on diet. And when that starts to grow over time, you slow the flow of blood to the heart. That results in heart disease. And when it gets plugged by either a piece of plaque that dislodges or a clot, that's a heart attack. And the downstream part of that flow, whatever tissue that blood was feeding, starts to die. And that's why a heart attack is so dangerous. The same condition, same mechanism occurs in the brain, then it's called a stroke. Again, and this, by the way, is a leading contributor to the leading cause of death, heart disease. That rise of surgical robotics that you saw before, Intuitive Surgical was going after this procedure and other minimally invasive heart procedures in the early 2000s. Little known fact is they were on the verge of bankruptcy because they were not succeeding until the urologist started using it, and then it really took off. So let's look at this market. It turns out everything is either bypass surgery or stents. The underlying problem, getting the plaque out of there, it's called atherectomy, removing the actual plaque, is almost never done. And there's another population here called no-option patients, which is not small. There's actually roughly the same number of no-option patients as prostate removal patients, which drove the explosion of surgical robotics. So there's a tremendous opportunity here. If we can get surgical robotics to treat this condition, you could really disrupt a massive amount of healthcare in a positive way. But you can't compete with stents. You see, there's actually companies right now that make stents that, for example, dissolve, and they're failing because you can't compete with a stent. If your stent costs 3 times as much, and you can prove that it's better, they're just going to go into the cheap stent anyway. And so our strategy is to actually go after these no-option patients. These are individuals whose arteries are so tortuous, you can't get a stent. There's no catheter that's going to go in and navigate their tortuous turning vessels, and they're not good candidates for surgery. But if you can bring the precision of robotics to safely and precisely walk through those arteries, take out the plaque in no-option patients, if you can do all those 3, you would potentially have a disruptive technology. First of all, there's no competitor. There's no competitive market. If you could do it for the no-option patients, you get your foot in the door in the clinic, and then the cardiologist, interventionalist, will start using it for all the other procedures. And you could potentially disrupt CABG, coronary bypass, and stenting. And by the way, I think it's just a matter of time before somebody does this. It's not if somebody's going to do this, but when and who. So our approach to this has been a little bit different. We've decided to sort of reinvent how catheters work. Catheters have been around. They've been in horses since the 1800s. And for the entire time, people have been pushing catheters at the tip. This is kind of what it looks like. You get this long, slender catheter introduced in a blood vessel, let's say the subclavian here, and it goes into the vessels of a heart under fluoroscopy. And you're pushing at the back end and trying to get control of the front end, and once you're going through a bunch of anatomy, that becomes complicated and difficult. So we decided to sort of reinvent this and say, what if we took our catheter, that's a catheter inside of a blood vessel, and instead of pushing it from the back end, we let it pull itself at the tip. So imagine this is a catheter walking through a blood vessel. And this little motion mechanism, this kind of inchworm motion, if you will, is predicated on those helices. So we're using that little helix, that spiral, because if you used a balloon, you'd block blood flow, and that's a heart attack. That's what we're trying to treat. But if you use the helix, you can anchor into the vessel and still have blood flow, so you're not cutting out on procedure time. And the idea is that this is a soft robot, so it's inherently soft, inherently compliant. You can't damage the blood vessels even if you tried. When you get to where the plaque is, you have some other degrees of freedom that will articulate and slowly start removing the plaque. I'll show you a technique for that a little bit later. For this, we're using hydraulics and McKibbins. I'll skip through some of this stuff for the sake of time. We've built a few of them. The basic idea is you're wrapping a tube with fibers, and you can make that tube turn to whatever shape you want and be very strong. Building them looks kind of like this. We have a little lathe that we hacked so that we can wind fibers onto them. We can model this thing. The model is actually pretty accurate for putting in pressure. So this is saline that's going in here. The relationship between volume and pressure is a fourth order polynomial, not very complicated. Now the question is, how do we get serial locomotion? The blood vessels of a beating heart, we're talking about like a 2 millimeter diameter. So this has to be small. There's no way we're going to get parallel actuation. We're not going to get 4 lines of pressure to independently control 4 or 5 actuators. We get 1. How do we get this motion out of 1 actuator, out of 1 line of pressure? And the idea was this. Imagine I had a little RC circuit. If I apply a square wave of voltage, this capacitor charges first, and then this one, and then this one. Very simple idea, passive circuit. And then if I discharge it, get it to 0 volts, this one discharges first, and then this one, and then this one. And by tuning the resistances, I could tune the timing of this thing. So our system was a mechanical system. This was our resistor. It was just a simple flow restrictor. So a little valve, a little set screw that pinches this, and is governed by the orifice equation. Fits the model pretty well, and you end up with a pretty hairy nonlinear model. Each p is a fourth order polynomial. But with that, you can optimize to basically say, what are the 2 settings on these 2 knobs? What are my 2 resistance values to get me the motion that I want that's most effective? And it works. So this is a large scale model. This is at just under a centimeter in diameter for the first work. But you can see it working under robotic control. And it was simple enough, actually, that you can drive it by hand. So this is actually being driven by a syringe and saline. All the parts are MRI compatible and disposable. It's very inexpensive. And so now the only challenge is to scale down, which is still a challenge, but doable. And we point out embodied intelligence. What you're seeing here is a fish. There's a well-known fact that if you take a fish, gut it, and maybe even take out its brain, you put it back in the water, it will swim away. It's this notion that most of the control, and also like in the 80s, there's some weird work on cats where they would decapitate a cat and put it on a treadmill, and it would still keep walking. And this notion is that there's, in mammalian control loops, there's embodied intelligence. You don't do like your brain doesn't close all the control loops. You do supervisory things like tell your limbs to walk, and they just magically do it because they have embodied intelligence. There's lower level control loops doing all the complicated stuff. As evidence in this example, you take out the central system and the lower level loops, they just interact with their environment to create swimming. And so our sort of contention is that this is the same thing going on in our little spiral mechanism here, that as long as you're putting energy in, you'll figure out how to locomote. There's no need for advanced sensing or control. All right, so I mentioned walking through anatomy. What about no option patients? So these are patients, again, whose anatomy is so tortuous, there is no single device that can navigate their anatomy. This is where 3D printing comes in. So we can get a CT scan. These are actually now available tools like from VMTK, the Vascular Modeling Toolkit. You get a CT scan, and they could, for example, compute the center lines automatically from the CT scan. So you can get the geometry of that particular patient, the really challenging geometry. Well, let's say from that challenging geometry, we have the initial shape of my catheter, which is always going to be a small cylinder as I can get it, and the final shape. So here I'm showing a spiral, but it could be any weird shape you want, any weird amorphous shape, right, that can conform that anatomy that's really unique. Well, so here's our idea. We're going to do inverse design. Instead of starting out with a mechanism or a manufacturing technique, we're going to say, no, here's what the patient needs. How do we get this thing to actually get built? Inverse design. Here's what they need. Make it happen. And here's the idea. If I know that initial and final shape, then for any point on that body, I can see how much local deformation there has to be, anisotropic deformation. If I know how much local deformation there has to be, I can back project that onto the material and say the material stiffness has to have these certain properties in that little pixel or voxel of material. Well, that's pretty exciting because it lets us go directly from a patient's needs to a blueprint, the ideal blueprint. If we can give this to a 3D printer, we can 3D print a patient-specific actuator. That would be ideal for this patient. This is the idea. And we've been sort of working with a group in chemical engineering on this. And then I'll kind of skip through this too. So we've talked about, so great. It looks like we could actually locomote through arteries and possibly do it in no-option patients. And keep in mind that the economies of scale are there to actually do this. There's a large number of these patients. The question now is, how do we remove the plaque? So we get there, how do you take stuff out? The excimer laser, this is the same technology in LASIK eye surgery. It's a fascinating technology. You get a pulse of ultraviolet light that is picoseconds in duration. There's some bubbling and stuff that happens afterwards, and it doesn't heat up tissue. A regular laser just cooks tissue. It's a thermal ablation process. This laser pulses tissue with light at such a high intensity that it disrupts the molecular bonds. The particles are smaller than a blood cell that result, and you get these 50 micron, you can basically mill tissue with a 50 micron accuracy. That's why they use to sculpt a lens. It doesn't heat things up. Well, this thing is FDA approved already. It was actually a big deal in the 1990s, and it flopped because it was a little unsafe. It's already FDA approved for use in patients to remove plaque. You can see one of them working here. And we had a really simple idea. So right now, the reason why this is not used is FDA approved for atherectomy. Clinicians do not like it because when you're using this thing, you can't see you can't see soft tissue. You're looking at basically an X-ray in real time. Soft tissues don't show up on X-ray. So you can very quickly lase through plaque and start lasing through the vessel, and now the patient's bleeding out, and you have an emergency procedure you have to do. So it's perceived as unsafe. So we said, well, what if during the off time, we have like 24 milliseconds. That's like a lifetime for engineering, right? What if we just query the light, we send some light down and look at the light coming back? Most plaque is visible to the naked eye. These are not small signals we're talking about. Our preliminary results show that we could actually, in real time, detect the difference between plaque and artery wall, at least for a specific patient. And then actually, we hook this thing up into the excimer laser. So what you're seeing here is the notion of an error-avoiding surgical robot. We have a surgeon, well, in this case, it's just a grad student, doing a mock task. The idea is the task is so easy, any human expert with decent visual acuity can sit down and do that task expertly. Now, this task is we're saying, so the idea is you only want to lase the white stuff and leave the yellow stuff, right? Anybody can do this. What we're showing here is that when you put the laser pedal on and you're just indiscriminately lasing everything, we can automatically shut it off when you get to the sensitive areas of tissue. So even if a surgeon is trying to make a mistake and cut tissue that they shouldn't be, this algorithm won't let them actually do it. And then we did a small user study where with 5 different people, 4 different trials, each we asked them to as carefully as possible lase and as quickly as possible as if they were trying to get out all this tissue, and showed that even on the super simple task, everybody is an expert, we could get improved performance. So you had lower errors, even though people should be making 0 errors, they're still making errors, and we can reduce those errors at that margin. So the clinicians got excited about this. We thought it'd be a little controversial, but they said no. We know it's hard. We actually want this now, in the operating room. All right, and I'll just wrap up with this. The final slide is kind of a completely left turn, big idea. what if robots, instead of us trying to incrementally improve surgery, because surgeons say they want a sharper scalpel. There's that classic quote misattributed to Henry Ford. If I asked people what they would have wanted, they would have told me a faster horse, right? But sometimes you could have different ideas. And the question is, maybe with robotics, we can actually do something drastically different. So surgery has been a subtractive manufacturing process. We give surgeons scalpels, and they traditionally take tissue out. What if we can give them a little wand that could add tissue back in the right location? And irrespective of human motion, a beating heart. And so that was kind of our idea to do dynamic bioprinting. And the field of bioprinting, by the way, is doing very well. There have been successful transplants into mice. So you can get stem cells from a mouse, grow an organ. There was a study, I think, in Nature on successfully transplanting uterus into 5 mice, and they could actually carry pups successfully. So this is some very early work. I'll just skip through this. But long story short, we were able to let's churn that down. Yeah, this is an iris, where you can 3D print directly onto freely moving human anatomy. Now we're not bioprinting people. We're actually working with Anthony Atala, who's a bioprinting sort of figure. They do the chemistry in the cells. What we're really interested in is tracking motion and getting a robot to subtract out the motion, right? And the application here would be for burn patients. So for burn patients, actually Anthony Atala has been doing this, and a group in Australia, they can take stem cells out of your stomach, make basically a little concoction, and for a 2nd degree burn, they could airbrush that on, and your tissue will spontaneously grow back. Now the downside is you can't get really good, you can't get thickness, and you can't get good geometries. But Tony Atala was actually really excited about this, because now you could potentially do this stuff in vivo. You could bring the benefits of bioprinting onto a living patient. So I think I will stop there, just to thank our sponsors and all the grad students that actually make this work possible. And I'll wrap up with saying that computational surgery. So we started this talk with Hunter showing up, applying the scientific method to surgery. And I think now there's kind of a new renaissance happening, because now there's so much more numeric and quantitative rigor penetrating the operating room with all these new technologies. I think we're poised with fields like computational surgery and robotics to have a new renaissance in that area. So with that, I'll say thank you, and I'll take any questions. Semmelweis, yeah.
And for you to know that and to continue doing what you're doing is pretty awesome. It's a character, a lot of data, but it still can work out well for you. So
right.
Congratulations on the character aspect. Suggestion with regards to your first part, I have a lot of relatives in the medical profession. If you ask off record who they would want in surgery
yes.
for their children, you'll get a much better response. Who you should focus on. Your last question is on urology. Is it because there's a high level of tort scenarios with the urology?
High level of what?
Tort, like litigation.
Oh, I see.
Why is urology the best place?
That's a great question. Yeah. So by the way, to the first comment, the story of Semmelweis is actually really tragic, because even though I think this is what you're referring to, even though he got legitimate scientific data, he was ridiculed for it, and for the rest of his life, I think he ended up losing. He had a really sad story. But urology is fascinating. So historically, urology has actually traditionally been a leader in a lot of technology. So they're the first endoscopic procedure, for example. Part of that is twofold. I think they have a culture of being, let's say, not risk averse. They're interested in new technologies and trying it out. And also, in urology, your chances of doing some really serious damage are in some ways way lower. Like if you've got, first of all, beating heart, it's very difficult to get in there. If you mess anything up, you start bleeding, that's a really serious condition, right? Whereas in urology, you can put things through the urethra or percutaneously and do some damage, and the patient will still be fine. So it tends to be a safer proving ground for a lot of these technologies. So I think the answer is twofold, is that it's easier to get it in there, and the culture is there where they actually really wanted to use it. And then the other reason is the Da Vinci robot didn't really meet the needs of what a cardiovascular surgeon wanted. You know, if you think about it, you have a stiff, dangerous tool next to a delicate beating heart. It's a bad design decision, right? Whereas in prostate surgery, first of all, they gave surgeons a wrist, which was a revolution. And in prostate surgery, it's really, really hard access. You've got a bone that you're contending with. You need to be able to reach around and start tying knots. And getting a wrist was just the best thing ever in urology. So I think that's part of why it was like such a good match for that particular robot that it took off. Thank you.
Any other questions?
Do you think that micro-scale robots would be better than large-scale robots in terms of like the parts and all?
Yeah, so that's a great question. There's a great slide by Paulo Dario, who's one of these huge figures in our field, where he kind of tries to map it all out. So open surgery was macro scale, and then biomedical, biological, cell biology was coming up at this cellular and nanoscale, and the future they're going to sort of meet together. And I'm kind of still in this mesoscale. You know, I'm still thinking about catheters roughly 1 millimeter in diameter, but there are folks working. So like Beth Sattler in our campus, she's working on gold macroparticles, but basically nanoparticles that you can sort of tune with to basically identify factors that would make them attracted to cancer cells, and then hit them with therapy. I think there's probably always going to be a place for macro and mesoscale stuff, especially in congenital defects. But I think the future is probably going to see a lot more of the nanoscale stuff. It's just hard. It's hard to get, and I think one of the fundamental limitations, and this is what Paulo Dario's group tried to do, is get stuff down. They had an awesome robot, for example. Bob Webster was involved in this, where you have a bunch of capsules in a cup. You drink the capsules. They self-assemble into a robot inside of your stomach, do a surgery, disassemble, and come out, right? And the fundamental issue they had was power. To actually get surgery done, you need a certain amount of mechanical power. You need force and displacement, and so you need that energy density. And that's why we're stuck with hydraulics. We think hydraulics, you have the highest energy density of any technology known to man, right? So higher than anything electromechanical. So if you need any forces, you're stuck with that. I don't think with a nanoscale you can necessarily get that accomplished. So for the procedures that you need to tear tissues out, ablate tissues, it's probably going to be good enough.
Any other questions?
All right. Thank you all.